right. So we're continuing to lay the foundation of the concepts of electromagnetism. So conceptual discussion of electromagnetism, and soon you'll get into the algebra and the trigonometry and the calculus and the problem solving, mathematical problem solving, and so on of this. But the ideas are abstract, and we're trying to make it so that it's not quite as abstract. At least we can visualize a little bit what's going on. So I want to reiterate some things that can be confusing. You can always come back to these. So where we're going here today, in this video right now, we'll finish the idea of electric charge. Then the next video, we'll talk about charge separation a little more, rubbing, batteries, electroscopes, capacitors, insulators versus conductors. Important ideas. Again, just nice, simple understanding. And then we want to talk about something that's also quite abstract and a profound idea that Michael Faraday introduced of fields. Electric fields, magnetic fields, we can even talk about gravitational fields, and electromagnetic field waves. So we'll get to that. But let's talk about electric charge. And so, you know, I had a little pet peeve when we talk about a set of things, we call them masses. And the reason we have them here is for that property of mass. But that's not all they are. They're objects that have mass. And so, too, we sometimes talk about charges, but what is that? There really aren't charges. They don't exist, but it's a shorthand for something. So let's talk. So let's talk about the object and the properties that the object has. So what I'd like you to do is pause and make a list of fundamental objects, sometimes called fundamental particles. I won't issue with that language. But fundamental objects, and what properties do they have? Atoms, neutral, balanced, neutral, polarized, positive ion, negative ion, microscopic. So pause for a moment and see what you can say about these things. Okay, good. So the more you do, scratch your head and process this, the better. I'm going to be giving you some puzzles to do this with too. So hopefully you came up with fundamental objects. An electron, which we use E minus, and black is often negative. So we've got that. What else is there? Oh, yeah, there's that proton. Now, remember last time I mentioned that protons really aren't entirely fundamental. It was discovered that they actually have parts. What are those called? Quarks, right? So there's sort of two up quarks and a down quark. And there's just 6 types of quarks. You can name them 1, 2, 3, 4, 5, 6. Or call them up and down and weird stuff. You can look that up. So a proton, we just call P. Okay, and then there's the neutron, also made of 3 quarks. 1 up, 2 down, 2 up, 1 down. Don't need to know that. But let's start here. And this is what is around us and what we are. And of course, if you smash them together, you get other particles and all kinds of cool stuff. So these are pretty fundamental, right? Now, what properties do they have? I want to make this point here, is that an electron has mass. So the mass of an electron equals, you can look that up, it's obviously incredibly small. An electron has the property of electric charge. So I can use, remember what I use for that? Either lowercase q or sometimes uppercase q. Often we'll use uppercase q for macroscopic objects. So you'll see this. But so this means how much charge q, not quantity, right? Could have made up, used c for charge, whatever, but we use q. And with the subscript e, that's the charge of an electron. And remember, in nice units, that's very easy. Is it positive or negative? Negative, how much? 1 fundamental unit of charge. And something that, go ahead and commit to memory as you do it. Just memorize it. Negative 1.6 times 10 to the what? Negative blank coulombs. And I'll let you go back and fill that in, right? Just fill it in. And when you do that, you'll get that. And you'll remember that. Okay, protons also have, Let's see. Protons have mass. How much mass? Well, about, so sometimes rough idea, 1,800 times the mass of an electron, which is nice because all this is the 1800s where historically a lot of this was figured out. Protons also have charge. The charge of a proton, which is exactly 1 E. So interestingly, much more massive, but the same amount of charge. Don't overthink that, just go with it. You'll see, those are very deep questions. Take them to grad school if you want. How much is that? Plus that 1.6 times 10 to the negative, right? This small number, this is a big unit. And again, what is that exponent? You remember it. Okay, cool. And I'm going to say more. Neutron. Has it got mass? Sure, it does have mass. So you've got a mass of a neutron, which is roughly equal to the mass of a proton, which is more. Look it up. If you do it, you'll remember it. And we'll use it. What about the charge of a neutron? The electric charge of a neutron is neutral, 0. Why? Deep question, as I said. So again, if Ben Franklin said why, or the early researchers said why, they'd never get in there. They just see what happens. And as you go through history, and as people went through history and explored, they found out that these guys have other properties that do other things when you get into quantum mechanics and talk about spin and things like that. So these are the properties. Now, how do we know about the properties? We're going to get to that in a second. So, and this is a measure of the property. When we get to a neutral atom, of course, you know that it's got some mass of the atom, equals whatever, and the charge of the atom is 0, because it's neutral. And in fact, that's true for both of these guys. The difference is, this is polarized, and if you remember our little discussion last time, that means that we can separate the charge a little bit, the electrons and the protons, by moving the electrons a bit. So we'll talk about that. So they still have mass, and they still have a net charge of 0, but we'll see that these can play a little differently, as we'll see. So a positive ion, what is a positive ion? Does it mean that you added more protons? The number of protons determines the type of atom it is, or the element. So if you're adding protons, that's nuclear fusion, and let us know how you do that. So what you're doing is taking away electrons. Atoms, fundamentally, the electrons are on the outside. We can take them away. If my hand loses some, my shirt gains some. If my shirt loses some, my hand gains some. Whatever it is. So it lost some electrons. Neutral means the same number of electrons as protons, right? Okay, it lost some electrons. And this one, of course, a negative means it gained some electrons. Now hold on, I know this is sort of basic, but just to think about this, I have a question for you. Which one has more mass? Suppose I have a positive ion of carbon and a negative ion of carbon. Which one has more mass? Pause. Bet $1,000. Well, this lost some things, and this gained some. Now, it's not going to be very much. So in your calculation, you might not worry about it, or you might. It just depends. But this gained some things. So the mass of a negative ion is greater than the mass of a positive ion. And that just gets us thinking about, oftentimes, almost always, not always, we're talking about more or less electrons when it turns to atoms. Okay, and then what about charge? Of course, it depends. We could say it's got 2 extra electrons, then it's got a charge of negative 2e, or 2 of those. Right? If it's a positively charged doubly, then you've got a lack of 2 electrons, and you end up with a net charge of plus 2e. So It's that easy in counting that sort of stuff. So yes, you've got the charge of the negative ion is equal to some number, some integer number, right? Integer number of E. What's wrong with that equation? Well, if it's a negative ion, then of course that's going to be negative. And of course, if it's a positive ion, positive integer number of E's. And so that's what we mean when we say charge is quantized. Of course, I mentioned quarks last time. So just make it a little less abstract by visualizing as much as you can this kind of imaginary picture of what's going on. So when it comes to objects, usually, we're talking about adding or taking away electrons or moving them about. So when we have conductors, we can literally move electrons from one side of something to the other. Remember I said metal atoms often have 1 to 4 free electrons on the outer part of the atom. The inner electrons are bound too tightly, but they're 1 to 4 just, will go off wherever. So that's what the key of a conductor. An insulator, the reason that this is designed this way, right? I can grab that and not affect this. It's an insulator, meaning that the electrons are bound pretty tightly to the atoms. And of course, different materials have different properties. You get into those details as you study them and need them. But we have conductors and insulators. So conductors, let's just say, often 1 to 4 free electrons. In metals, you can have fluids that are ionic fluids. You can have gases that are ions, and you have plasmas, and it gets complex. But this foundation makes it at least, somewhat concrete, at least in our imagination. These, all you can do in the insulator, now it's true, you expose it enough, you can start ripping off electrons, but in the insulators, generally the electrons in the atom stay in the atom, but they can lean. Or what do I want to say? Lean. Can shift, let me say. To one side or the other. So, let's talk. We'll get into that next time. So, to finish this off, hopefully this is not too bad. Doesn't have to be hard, just go with that. How do we know how much mass something has? Well, if you recall last time, we could see how much does it resist acceleration. That gives us a measure of the mass. So how much does the spring stretch to cause a certain acceleration? And that's measuring its inertia in a non-equilibrium situation. It's accelerating. Or you can have a spring balancing mass. So how much does the spring stretch to balance the pull of gravity? Pull down of gravity, which is magical, nothing touching, really weird, and then the pull up from the spring in an equilibrium situation where the forces are balanced. Those are two very different properties of mass, and you get the same answer either way. Less mass. So what have I got here? Property mass, the force that it creates and feels is the force of gravity. And it also plays the role of inertia. But that's not force. So if it's got more mass, it's got more force, and it feels more force. It gets pulled down harder. So one of these gets pulled down a certain amount. This one gets pulled down the same amount. Put them together, pulled down twice as much. Somehow, we're letting go. Like, how does that happen? So we'll talk a little bit about that. We'll talk about fields, and then I'll mention Einstein just briefly. So what about this property we call electric charge? which we can use Q or Q to refer to as a variable mathematically how much electric charge the thing has. And of course that is related to the electric force. And so we can set up, again, it's a force, and you might put an E down there or EL, whatever. But interestingly, gravity G, or I kind of like the capital G, whatever you want, whatever works. This is always an attraction, as far as we know. This can attract and repel, so things get a little more complicated. And then there's the other force that we're going to be studying in this course, which is the magnetic force. And where does that come from? A magnetic charge? That's complicated. We'll get to that. We'll bring that aside. But I will say that this moving electrically charged objects are one of the sources of a magnetic force. And we're going to get into that when we get into all the different aspects of electricity and magnetism and the multiple ways that you can create these things. So if it's got more charge, it's going to experience more force. So let's go over here real quickly. And yep, we're almost there for this one. So I can take this, say, and do something. Is that let's go here. Let's see if I can get that. So it's not working very much. So I can conceptually get a sense I'm not getting a lot of charge. Maybe I need more charge here. Now this is an insulator, so whatever electrons either take off or in this case put on, they're going to stay right there. So if I do this side, it's no good. I got to do that side. Maybe I'll do this side right there. Try to do a little bit there. Let's see if I can get that. A little bit push. It's not very good. That's it. There's something, right? So it can be, the point here is it can be tricky, and if there's humidity in the air, that can affect it too. So setting up experiments carefully is a tricky thing. But you can then start measuring how much force do I get, and then in what direction is that force. So you can imagine people have been busy working this out. But keep this framework in mind, and we're going to get into how much, what are the mathematical equations for the direction and the strength of each of these forces, and that property which is creating these forces. And that's an interesting mix of stuff that is in many ways summarized by these, we'll keep wearing this for the next couple of videos, Maxwell's equations, and something called the Lorentz force. One last thing is we're also going to be analyzing certainly force vectors, but you can, as you know from your mechanics course, you can also analyze what goes on, not in terms of forces, but in terms of what? Energy, which is directly related to forces, we said today. It's another way of reframing that those interactions. So I think that's good. I hope that's clear. As you use it, it'll become clear. So don't sit here and obsess about this too long. Move on, come back, and let's play with some puzzles next time.